Hello everyone, myself Pathik DASBAIRAGYA, first semester student of ECE department in Cooch Government Engineering College. And my topic is about amplitude modulation and frequency modulation. Amplitude modulation. Introduction to amplitude modulation. Amplitude modulation is a technique used in electronic communication. It involves varying the strength of carrier wave in proportion to the information signal. The method is widely used in amplitude modulation, radio broadcasting, and other communication systems. Basic concepts of amplitude modulation. A carrier wave is a constant frequency wave that carries the information signal. The information signal modulates the amplitude of the carrier wave to encode data. The result is combination of carrier and sideband that represent the information. The mathematical representation of amplitude modulation is S of t equals to AC plus AM cos 2 pi FMT into cos 2 pi FCT. Variables in these equations are AM. AM is the amplitude of the modulating signal AC. The amplitude of the carrier signal FM. The frequency of the modulating signal FC. The frequency of the carrier signal. Explanation. Amplitude modulation is a technique used to transmit message using radio carrier wave. In amplitude modulation, the amplitude of the carrier wave is varied in proportion to the message signal. The modulation index in this is the ratio of the maximum amplitude of the message signal to the maximum amplitude of the carrier signal. Advantages of the amplitude modulation signals are simple transmission and reception. Amplitude modulation signals are easy to generate and detect using simple circuit, making them cost effective. The second point is cost range transmission. Amplitude modulation signal can be travel long distance, especially at lower frequency, and can reflect off the ionosphere, making them suitable for long range communications. I shortwave radio compatibility with analog system. Many legacy communication systems rely on amplitude-based signal, ensuring backward compatibility. Bandwidth efficiency. Amplitude modulation signal typically requires less bandwidth compared to frequency modulation signals, making them useful where bandwidth is limited. Multiplexing possibilities. Amplitude-based signals can be used in multiplexing techniques such as frequency division multiplexing (FDM) to transmit multiple signals simultaneously. Easier signal processing. Amplitude modulation-based signals are easier to process and analyze with simpler hardware, reducing cost and power consumption. Amplitude modulations have several disadvantages, including susceptibility to noise. Amplitude modulation signals are easily affected by electrical noise and interference, since noise primarily affects amplitude. Low efficiency. A large portion of the transmitted power is concentrated in the carrier signal, which does not carry useful information, leading to inefficient power usage. The third point is limited sound quality. Amplitude modulation has a lower bandwidth, typically around 10 kHz for commercial broadcasting, which limits audio quality compared to FM. Fourth point is fading issue. Amplitude modulation has experienced fading due to multipath propagation, where signals take different paths and interfere with each other. Higher distortion. Amplitude modulation is more prone to distortion due to non-linearities in transmission and reception. Shorter transmission range in daytime. High frequency amplitude modulation signal rely on ionosphere reflecting for long range transmission, but this effect weakens during the daytime, reducing effective range. Applications of amplitude modulation. Amplitude modulation is predominantly used in commercial radio broadcasting. It is also utilized in aviation communications and two-way radio system. In addition, amplitude modulation can be found in some television audio transmission. Modulation process. The modulation process requires a modulator which combines the carrier and information signals. The resulting amplitude modulation wave is then transmitted through an antenna. At the receiver, demodulation is performed to extract original information from the carrier. Demodulation techniques. There are several methods for demodulations in amplitude signals, including envelope detection and synchronous detection. Envelope detection is the simplest method, relying on the amplitude changes to the receiver's signal, and synchronized detection provides better performance in terms of noise immunity, but it is more complex. Future of amplitude modulation. Although digital modulation techniques are gaining popularity, amplitude modulation remains an important part of the communication landscape. Advance in technology may lead to improved amplitude modulation transmission methods to reduce noise and enhance quality. Researchers are also exploring hybrid systems that combine amplitude modulation with digital techniques for better efficiency. Conclusion: amplitude modulation is a foundational technology in the field of communications. Understanding its principle and applications help appreciate the evolution of modern communication systems. Despite its limitation, amplitude modulation continues to be relevant and effective in various applications today. Frequency modulation. Introduction to frequency modulation. Frequency modulation is a technique used to encode information in a carrier wave. It varies the frequency of the carrier signal in accordance with the amplitude of the input signal. Frequency modulation is widely used in radio broadcasting, telecommunications, and signal processing. Principles of frequency modulation. In frequency modulation, the frequency of the carrier wave changes based on the instantaneous amplitude of the modulating signal. The result is in a more robust signal that is less susceptible to interference. The deviation of the frequency from a carrier frequency is known as frequency deviation. The mathematical expressions for a frequency modulated signal is given by S of t equals to AC cos 2 pi fct plus beta sin 2 pi fmt, where S of t equals to a frequency modulating signal, S equals to carrier amplitude, F equals to carrier frequency, Fm is equals to modulating signal frequency, beta equals to modulation index, defined as beta equals to delta f by Fm, where delta f is the frequency deviation, sin 2 pi Fmt is equals to modulating index signal. Explanation: the instantaneous frequency of the frequency modulation signal varies based on the amplitude of the modulating signal. The modulating index beta determines how much the frequency deviates from the carrier frequency. Unlike amplitude modulation, where amplitude changes, frequency modulation keeps a constant amplitude but varies the frequency. Advantages of frequency modulation. Frequency modulation provides improved signal quality and resistance to noise compared to amplitude modulation. It allows for better fidelity in audio transmissions, making it ideal for music broadcasting. Frequency modulation also supports stereo sound, enhancing the listener experience. Applications of frequency modulation. Frequency modulation is extensively used in frequency modulation radio broadcasting, where it delivers high quality sound. It is also utilized in television sound broadcasting and two-way radio communication. Additionally, frequency modulation is used in technologies like analog and digital synthesizers for sound generation. Difference between frequency modulation and amplitude modulation. Unlike amplitude modulation, frequency modulation varies the frequency rather than the amplitude of the carrier wave. Frequency modulation is less affected by signal degradation and has a higher signal to noise ratio. Amplitude modulation is simpler and requires less bandwidth, but frequency modulation is preferred for high fidelity audio applications. Bandwidth requirements. The bandwidth of a frequency modulation signal is determined by Parsons rule, which states Pw equals to 2 into delta F plus Fm. The bandwidth requirement allows for adequate transmission of the information being encoded. Frequency modulation generally require more bandwidth than amplitude modulation signals, which can affect the choice of modulation in certain applications. Demodulation of a frequency modulated signal. Demodulation is the process of extracting the original information from the modulated signal. Common demodulation techniques for frequency modulation include slope detection, phase locked loops, and Foster Seeley discriminators. Proper demodulation is crucial for maintaining audio quality and signal integrity of frequency system. Challenges in frequency modulation. One of the challenges with frequency modulation is the need for larger bandwidth compared to other modulation methods. Frequency modulation signals can also experience distortion if the modulation index becomes too large. Additionally, multi-path interference can affect signal clarity, leading to fading issues. Future trends in frequency modulation. Advances in digital signal processing are enhancing frequency modulation techniques for better performance. The integration of frequency modulation with digital technologies may lead to new applications in telecommunications. Future research may be you focus on improving bandwidth efficiency and mitigating interference in frequency modulation systems. Thank you.